So it's
So the next week, I suggest. So can I share my slides now?
yes.
It will unshare Professor Simpi's. It will stop sharing Professor Simpi's slides. Is that okay? Is that lecture over?
I think there is some confusion. Professor Shimpi wants to present.
No, Akshay, I just checked the schedule.
Yes.
Professor Sarkar's, the slot is Professor Sarkar's.
I know. Professor Shimpi is scheduled for tomorrow morning.
Yeah, tomorrow morning.
Yeah.
Does
Professor
he know?
Shimpi, are you? I think he got confused. Let me just call him. Professor Shimpi, you are scheduled for tomorrow morning. Okay, I think Professor Sarkar, now you can start. Apologies, Professor Shimpi, for the confusion. I'll send you an updated schedule.
Is the slide visible?
Yes.
Okay. Okay, fine.
So you can start whenever you are ready.
Okay. So shall I start now?
Yes, please.
Okay. So let's start. Thanks, Professor Akshay, for giving me this opportunity and for the introduction. So I teach chemical engineering here. I'm an associate professor in Department of Chemical Engineering. So I'll be giving a very brief introduction to multi-objective optimization. So So this is what I have decided. So because of the, only 1.5 hours and multi-objective optimization is quite, so what I have thought is I'll give you a very brief introduction. I'll try to bring a parallel between single objective optimization and multi-objective optimizations, focusing only on the very basic stuff of multi-objective optimization. And we'll give you an example on how to solve a multi-objective optimization problem using a MATLAB function that is available called GA multi OVG. Okay, so whatever I say, perhaps almost everything will be found in this excellent book called Multi-Objective Optimization Using Evolutionary Algorithms by Professor Kullan Maideb. So I'll give you a very, we'll start with what is optimization, then compare single objective optimization and multi-objective optimization. So we'll try to find out why we need multi-objective optimization. and some basic definitions of basic stuff associated with multi-objective optimization. Then 2-3 methods for solution of multi-objective optimization, but we won't be able to go into details, but give you a sketch of those methods, and then spend some time to show you the application of this MATLAB function for solution of any multi-objective optimization. So hopefully after this lecture, you will perhaps be able to solve simple multi-objective optimization problems using this MATLAB function. Okay, so let me start with a very simple example on single objective optimization. Let's think of designing a cylindrical vessel with leads, and the vessel must have a specified volume V. Okay, so the parameters that we have in my control, that means that the decision variables, that means the variables that we can vary, my independent variables, are length and diameter of the tank. Okay, you also know that this length and diameter related to each other. So I want to design a cylindrical tank which has both the leads with a specified volume, such that the cost of the construction is minimum, cost of the design is minimum. We only the cost of the material. So if I say that, it means that basically the amount of material that is involved, that means the area of this lateral area of the tank as well as the surface area of the top and bottom, that we add, that we need to minimize. Because the cost of the tank is related to its surface area. Okay, that is the amount of the material required. So let's define CS as the cost per unit area of the tank's lateral area, tank side, and CT is the cost of unit area of the tank's top and bottom. So how will you mathematically pose this problem? So in any optimization problem, we'll have an objective function, which is also known as cost function. And then we may have set of constants which together decide the feasible region over which you are going to find the decision variables that solves the problem. So here, obviously the cost function is the natural, you have the natural choice that the cost of the tank. So cost of the tank is directly related to the surface area. So total surface area, which is a function of these decision variables D and L, becomes my objective function. So note that CS is the cost per unit area of the tank side. Okay, so the lateral area is pi dl. So multiplied by this unit cost factor gives you the cost for this lateral side. And then pi d square by 4 is the area here. So plus pi d square by 4 at the bottom. So you add this 2, it becomes pi by 2 d square multiplied by the unit cost of the area of the tank's top and bottom. So this gives you the objective. This gives us the objective function for this problem. So we have constants. The constant is this, that the design, the tank will have a specified volume. So we have an equality type constant V equal to pi d square L by 4. You can also say that the volume will have a minimum certain amount of volume, right? So the volume must be greater or equal to some specified value. So that will be V greater or equal to, say, V specified, V given. And of course, this non-negativity restrictions are there because these are the physical quantity, diameter and length. So they cannot be negative. So this is a standard formulation for this single objective optimization problem. And we have a host of analytical and numerical techniques for solutions of single objective optimization problem, which you can apply and come to the values of DNL. You can also note here that since this V is given and L and D are related to V, so it is possible to eliminate one of these variables and then convert this objective function from a function of two variables to a function of one variable. Okay. So now, before we go further, let's take a minute and see that what are the different types of optimization problems that can exist. There are various ways of classifying these optimization problems. So one is shown on the screen here. It's based on convex optimization problem and non-convex optimization problem. So convex optimization problems will have the objective function as convex functions, and the feasible region is the convex region, which the convex problems can again be classified as linear programming problem as well as nonlinear programming problem. Linear programming problem are always convex. Nonlinear programming problems can be convex as well as non-convex problems. Okay. So again, based on your decision variables will be defined on the continuous domain, or they are the continuous variables, or they are discrete variables, or some of them are discrete and continuous. Again, you may have various ways of classifying these optimization problems. Suppose you have a linear programming problem here. A linear programming problem will have the objective function linear and all the constants are linear. And let us say that all the decision variables are continuous variables. Now, if you have some of these decision variables are integer and some of the the remaining decision variables are continuous, we have mixed integer linear programming problem. The same thing holds true here also. If the nonlinear programming problem, some of those decision variables take on integer values, some of the decision variables take continuous values, we have linear programming problem. We can also have pure integer programming problem. Okay. So this is there are various ways of classifying these optimization problems. Another ways will be stochastic or deterministic. Stochastic optimization problem or deterministic optimization problems. In deterministic optimization problems, your data are certain, but the stochastic optimization problem, you have only probabilistic information on the data. Now, let us now formally define a general single objective optimization problem. So we'll have an objective function and we'll have constants. So let us consider an objective function in n variables. So x is the vector of n continuous variables and f of x is the objective function. So you want to minimize this objective function subject to certain set of constants. Now constants may be of two types: equality constants and inequality constants. So without any loss of generality, you can consider the inequality constants are less or equal to type, because if some constants are less or equal to type and some constants are greater or equal to type, you can always convert one to another. Let us say you have a greater or equal to type constants. You just multiply both sides by -1. That will be converted to less or equal to type constant. So we can pose a general single objective nonlinear programming problem as this, where we assume that we are minimizing an objective function in n variables. The objective function may be nonlinear. In general, we are not posing any restrictions on linearity or nonlinearity, right? So it may be a nonlinear function in n variables. Same is true with the constants. So we can classify the constants as two types: inequality constants and equality constants. So if this x takes on only continuous values, we have a general nonlinear programming problem. If some of these x take on integer values, we have mixed integer nonlinear programming problem. Now, what does this constant do? The constants will define the feasible space for these decision variables. Note, in this formulation says that we are going to find a set of x which minimizes this function as well as satisfies this constant as well as this constants. So we may have p number of inequality constants, we may have m number of equality constants. It is not necessary that every problem will have all types of constants. Some problem may have both inequality and equality constants. Some problem may have only inequality constant or only equality constants. So when you find out this x that minimizes fx, this x must satisfy this inequality constant as well as equality constants. Note that these inequality constants and equality constants together define a search space. So x must lie on that within that search space. So it is important that x be feasible to become an optimal solution to this problem. So that is what the feasible points means, that x will satisfy these constants. For example, let us consider a two-dimensional problem. Two-dimensional problem means your objective function is a function of two variables, x1 and x2. And we have these two constants, g1 and g2. g1 less or equal to 0, g2 less or equal to 0. You also have, I have not shown here, let us say we also have x1 greater or equal to 0 or x2 greater or equal to 0. In that case, note that this white region is defined by x1 greater or equal to 0, x2 greater or equal to 0, as well as g1 less or equal to 0, g2 less or equal to 0. So this white region is the feasible space for this optimization problem. For example, in this schematic, you have this gx less or equal to 0 is defined by this, but this equality constants is this. So the solution has to lie on this because it has to satisfy the equality constant as well. You can see it from here. Let us say we are minimizing a function. We are minimizing a two-dimensional function. So we can plot this contours of function contour means, let us say 20f equal to 20 here. So all the values, all x1, x2 that lie on this will give you the objective function value 20. Similarly for 15, similarly for 10, so on and so forth. So if you are minimizing, and if this is the point corresponds to f equal to 0, that becomes an unconstant minimum. That will be the minimum of this optimization problem when you do not have any constant. Now what happens if you have a constant? So you have a constant like this. So this constant is g less or equal to 0. Sorry, g less than 0, let us. G less or equal to 0. G less or equal to 0. this is the feasible region. Let us say this is the feasible region. On the left side of this line, on the right side of this line is the feasible region. On the left side of this G, x equal to 0 is the infeasible region. So the solution must lie here in this region. But where? Since I'm minimizing a problem, so I must look for minimum value of the objective function. As the diagram shows that as you go in this direction, the contour, see, indicates that they corresponds to higher and higher objective function value. So definitely I will be looking minimum in this direction. And I can go only up to this. Because if I cross this line, I'll be entering infeasible region. So I basically have to look for that contour which passes through this point. So that may be say 12. So that is the constant minimum. So presence of constant basically defines your search space. Now, in case of single objective optimization problem, so typically we can have a convex function or we can have a convex function. If you have a convex function or concave functions, you know that you'll have a unique minimum, okay, or maximum. You may have a function like this, which has several local minimum. This is one, this one, this one. All these are local minima. The base local minimum is known as the global minimum within this domain. Your single objective function, as I told you, can be a function of n variables. So the easiest, the simplest is the simplest multivariable function will have two variables as shown here. So we'll find out this solution as the minimum solution. Or if you have, you know, multimodal functions, you'll have these as the local maximas. And one of these will be the global maximum also. These can also be expressed as contours on the two dimension. Now, all these cases for single objective optimization, we have the standard tools, standard algorithms for solutions of these optimization problems. In case of single variable optimization problem, you can even take that, you know that if you take the derivative, the derivative will be equal to 0. Here, in terms of derivative, this is a two variable function. So instead of the derivative of the function, you will have the gradient like dy df, it is f. So del f del x equal to 0, del f del y equal to 0. So simple analytical functions can be solved in an analytic way. Is making use of the optimality, simple optimality condition of the optimization problems. The complex problems can be solved numerically, and we have several numerical optimization techniques for solutions of single variable optimization problem. Now, let us just consider that instead of asking what will be D and L such that the total surface area is minimized. This is what we have been asking. That instead of that, find D and L, diameter and the length of the cylindrical tank, such that the total cost is minimized or the total area is minimized. Now, if I ask that how to minimize both this lateral area. Sorry, it will be how to minimize both the total area as well as the area of the top and bottom, subject to the constants that volume will be greater or equal to some specified volume. Now immediately that you won't be able to solutions because you have several designs. Look at this problem, you'll have a single solution here. I am minimizing this, but now I minimize the total. That means I minimize this, but also simultaneously minimize the base area or the stop, the sum of the stop area and the bottom area, subject to some volume constant. Maybe say V greater or equal to V max. So now immediately you recognize that there can be several such designs and it may be difficult to choose which one is the optimal solution. So what I'm trying to say is that most problems in nature will have several objectives to be satisfied. And oftentimes, these objective functions may conflict each other. For example, let's consider the design of a bridge for which you want to minimize its weight, minimize the cost, and maximize its safety. Note that all will not go hand in hand. If you want to maximize one objective, you have to compromise with the others. If I want to, say, maximize the safety features, I cannot minimize the cost at the same time. So enhanced safety features will come at a cost. But all these things are important objectives, which as a designer, you would like that your design satisfies all these objectives simultaneously. Consider a manufacturing plant. So you want to maximize profit, you want to minimize energy requirement, you want to minimize environmental pollution because there are strong regulatory requirement. You have to minimize the environmental pollution. You want to maximize safety of operation. You want to minimize cost of operation. So it's not like if you maximize one objective function or minimize one objective function, others also get maximized or minimized. Some objective functions will conflict with each other. And most problems in nature will have such conflicting objectives to be satisfied. So I could think of this for an design of aircraft. So perhaps you would like to minimize its weight, minimize the cost, maximize capacity, maximize cruising speed, maximize comfort, maximize safety. We have lots of mobile phones, right? So a choice is not always easy because you want to maximize display, you want to maximize camera quality, we want to minimize power consumption such that battery life is improved. Also at the same time, you want to minimize cost. So there are several such problems, important real world problems, which will have several goals to be achieved and they'll possibly conflict with each other. Now, since we know how to solve a single objective optimization function, single objective optimization problem, we can think that we'll convert these several objectives that we have to a single synthetic objective, by taking and weighted sum of these individual objectives. So for example, if you have just two objectives, F1 and F2, and I am simultaneously optimizing, minimizing, or maximizing, or one maximizing, one minimizing F1 and F2, that multi-objective optimization problem can be converted to an equivalent single objective optimization problem by this weighted sum method. So you take W between 0 to 1 and make a weighted sum like this. This is one approach. Another approach, maybe you transform all the objectives into constants except one. So we have several objective functions. Let us say I only minimize the cost and then set these objective functions as constants. So these are two classical ways of handling multi-objective optimization techniques, but they have their own problems. And we'll discuss some of those. And we'll try to see that it's a good idea to solve a multi-objective optimization problem as multi-objective optimization problem instead of artificially converting it to a single objective optimization problem. So let us, this example is taken frequently. Again, this example is there in Dave's book. So think of buying a car. Okay. Let us focus on this. So there are several cars available. Okay. And let us say we have two objective functions. That means when we are deciding to buy a car, we'll consider two things. One is what is the cost of the car and what is the comfort. Let us say comfort I express, see cost is easy to express, right? So let's say these are in Indian rupees, whereas comfort, I have to, some hypothetical percentage is given as comforts. Say something we have in mind which is 100% comfort, and then based on that we define various level of comforts, assign those to different designs of cars. So cars are available at various prices and they are all associated with different level of comforts, and it's not a it will be very reasonable. More expensive is the car and higher is the comfort. Now we have to buy the car considering both cost and comfort simultaneously. See, if we consider only cost as the objective, so this will be the solution. I mean, the car which comes with this cost I'll buy. So every buyer will buy this car. So manufacturer will make these cars only. But there are rich buyers, there are very rich buyers, right? For whom comfort is perhaps the only objective. So if comfort is the only objective, then perhaps this will be the design and this will be the natural choice. But since it is always a trade-off between cost and comfort, we have these various designs with various level of comforts. Now let us consider this design. Or this design, or for that matter, this design. So all these designs, if you consider, design A comes with this cost and gives you this level of comfort. B comes with this cost and comes with this level of comfort. C comes with even higher cost and also gives higher degree of higher level of comfort. Now see, when I simultaneously consider cost and comfort, both the objectives simultaneously, is very difficult to decide whether A is better than B or B is better than C, and so on and so forth. Because A, if we simultaneously consider cost and comfort, and it will be natural for me to consider that I want to minimize the cost and I want to maximize the comfort. Because otherwise you will either have this solution or this solution. So the design A is superior, say, compared to B in terms of cost objective, but inferior with respect to B and C in terms of comfort. But let us say we have a design here which gives you the same amount of comfort as A gives, but comes with a higher cost. So if definitely A is better, even if considering both the objectives simultaneously. But the same we cannot comment about A, B, and C. So this A, B, C will be known as non-dominated solutions. That means these solutions are neither inferior nor superior with respect to each other when you compare both the objective functions simultaneously. One may be superior in one objective function, but then perhaps it is inferior with respect to the other objective function. So these non-dominated solutions or non-inferior solutions are those solutions which are neither inferior nor superior with respect to both the objective functions when considered simultaneously. So in multi-objective optimization problem, we would like to obtain as many such problems, as many such solutions as possible. Like A, B, and C, which gives me different cost, different comfort levels, and none of them are inferior or superior with respect to each other when both the objective functions are considered. So my objective will be to find out as many such solutions as possible where a trade-off between this cost and comfort exists. But when you consider all the objective functions simultaneously, none of them are inferior, superior with respect to each other. So what will you do with this information? So when this information is available with me, then it becomes easy for me to make an informed choice. Because in real life, your purchase of that car will involve on many other factors. Say total finance available to buy the car, fuel consumption, depreciation value, road condition, then social status, after sales service, so on and so forth. So as an optimizer for a multi-object automation problem, we'd like to have as many non-dominated solutions as possible. And then we'll decide which the solution cup based on other considerations. For example, if you are an optimization expert and a financier has given you this task that you need to help him or her in this purchase of this car, you will keep all these trade-off solutions, and that will help decision maker to take a decision, because ultimately you are going to buy one car. But deciding which car to buy, I must know what all the other alternatives are available. And non-dominated solutions are those alternatives which are, within quote best when all the objective functions are considered simultaneously. Now, why we have to consider both the objective functions simultaneously, we perhaps could get some idea. So to know a little bit more about that, let us ask what is the difficulty in combining these objective functions and get a single objective function like those weighted sum. See, in general, there exist different conflicting goals for an optimization task, and we have seen many such examples. Now, when you combine them, like this weighted sum method, into a single objective function, you are basically artificially reducing the number of those conflicting goals. And the correlation between these objective functions may be very complex. The different objective functions or different objectives are not always commensurable, means that these objective functions may be measured in different units on different scales, which will make it difficult to combine them into a single synthetic objective. For example, how do we combine cost and comfort? They are two different things. So, while by combining these objective functions, multiple objective functions into a single synthetic objective functions, you would get a solution, of course. You'll get one single solution, but you may lose on many things. So it is always best to solve a multi-objective optimization problem as a multi-objective optimization problem where your main goal will be to obtain all the non-dominated solutions associated with the problem. Again, let's take a simple example, another simple example. Suppose I'm planning for a night stay, say in a city, right? And I had, so I have to rent a hotel. So this is the hotel types I have, and these are the prices I have to pay for. So you compare 0-star hotel and 1-star. See, if the prices are like For 0 star, it is 1,500 and 1 star, it is 2,000. I'll perhaps prefer the 1 star. And if the 4-star one cost 4,000 and 5 cost 7,000, and if I have to compare these two, I'll prefer 4-star. So it is important to know how much value we'll put on an extra star, and that will depend only when you know what are all the alternatives that are available. So combining the multiple objectives into a single objectives is like you are combining different objectives without knowing the alternatives. The same thing is true for the other approach of optimizing only one objective function and considering all other as constants. You are doing that before all the alternatives are known. So there is difficulty in combining the objective functions. So to summarize, for single objective optimization function, so you find, say, this is the objective function line, let us say. So if you are maximizing, perhaps, let's say this may be the optimal solution, minimizing this may be the optimal solution. So typically, there will be only one single solution that gives the best objective function value. But for multi-objective optimization problems, the scenario is with similar to that purchase of the car. So consider a multi-objective optimization problem with two objective. Yes.
Sir, I am having one question, sir. Can I ask, sir?
Sure.
So I am Aditya Tiwari from Indore. Sir,
Sure.
I just want to ask that in this the example which you have just shared of hotel. So
Yes.
there only we have taken the price of the hotels. In the previous example, you have
We also
of
considered comfort.
purchasing of the car. Yes, comfort. So can we also that thing also be considered over here, no, sir? Comfort and price can be taken over here also, no, sir?
Yes, of course. For that example, idea is to, before I take, idea is just to convey that idea I wanted to convey is, before I can take a decision or I can take an informed decision, I must know all the alternatives that are available.
Yes, sir.
Okay. So so coming back to this, so when you have multi-objective optimization problem, let us say with two objective functions, and I'm minimizing both the objective functions. And let us say these are the feasible solutions. So now let us compare, compare these two solutions. Now I'm minimizing both the objective functions. Okay. Now consider this solution and this solution. Again, you see this is superior with respect to this. Just comparing these two. This is superior with respect to this because you have this has less value for F2 compared to this, but more value for F1. And since we are minimizing both, you know that the solutions around this, right? Solutions around this will be, the most preferred solutions because we are minimizing both. Now, if I if I compare these two, which is the furthest from here, right? I mean, I do not have any solution here. Now, if I compare these two, can I say which is better? I cannot, because this is, if you compare these and these, this solution is better than this in terms of F2, but inferior in terms of F1, because this F1 has a lower F1 value for this. So I cannot say which one is better when you compare these two solutions. And that decision is based on comparison of both the objective functions simultaneously. Note that you may have any number of objective functions, and similar comparison has to be done in higher dimensions. Let us restrict ourselves only to 2 dimensions so that the concepts are easy to understand. So this is one key difference between the single objective optimization and multi-objective optimization. You typically will have a single optimal solutions. It is not generally true, because see, you may have a multimodal function. The function one function, I think I've shown you, and slides also will be showing. But generally, typically we'll have a single solution. But in case of multi-objective optimization, so the concept of this dominance is very important in case of multi-objective optimization. We'll formally define what we mean by dominance in just maybe 1 or 2 slides after this. So this is another difference between single objective optimization problem and multi-objective optimization problem. Consider the decision variable space. So we have, let us say, objective functions in 3 variables, x1, x2, x3. So we have a 3D space. And let us say we have 2 objective functions, f1 and f2. So this f1 and f2 two objective function will constitute a 2-dimensional objective space. And note that every point, and let us consider this shaded region as the feasible decision region. Feasible decision region means this region is the region which is obtained by all those constants. That means any x is a vector having elements x1, x2, and x3. So any point within this shaded region is feasible. That means that satisfy all the constants. Now every point in this feasible region will have value for one value for f1, another value for f2. Right? Because these objective functions are nothing but functions of these decision variables. So a point on these decision space will correspond to a point in this objective function space. So all these points in the feasible decision region will have a corresponding point on the objective function space. So that will also give you a feasible region for the objective function space. So there is 1:1 mapping between the decision variable space and the objective function space. Note that for single objective optimization problems, we do not have this objective function space. The dimension of these spaces will depend on the dimension of the variables and the dimension of the objective functions. A multi-objective optimization problem will have at least 2 objective functions. So we'll have at least a 2-dimensional objective function space. And each solution in the decision variable or each feasible point in this decision variable will correspond to a point in the objective function space. Now, looking at some of these aspects about this multi-objective optimization problem, let us redefine what do you mean by optimization or optimization problems. So optimization is the task of finding one or more solutions which correspond to minimizing or maximizing one or more specified objectives and which satisfy all the constraints, if any. So I repeat, optimization is the task of finding one or more solutions which correspond to minimizing or maximizing one or more specified objectives which satisfy all constraints. In case of single optimal, we'll have single and solution. We'll call the optimal solution. On the other hand, a multi-objective optimization task considers several conflicting objectives simultaneously, and in such a case, there is usually no single optimal solution, but a set of alternatives with different trade-offs. We call these as non-nominated solutions or Pareto optimal solutions. And the task during any multi-objective optimization problem is to find these Pareto optimal or nominated solutions. You have seen that there was a line drawn for this car purchase problem on which point A, B, C, etc. was lying. That dotted curve, that means that curve on which all these non-nominated solutions were lying as Pareto optimal problem. We'll come to that. Okay, so this we have optimal solution. Okay, so that's the question. That is what I'm going to we are going to talk now. So despite the existence of multiple optimal solution in practice, usually only one of the solutions to be chosen. Let's just again think of this car purchase. Okay, you will have several designs, several trade-offs are known, but you are going to buy only one car. I mean, if it is for personal use. If you are a car seller, it's a different story. Yes.
Professor Sarkar, there is one question in the chats. How to choose one optimal solution from many optimal?
That is what we are going to discuss now. Yes. Yes. Okay. So that is another another difference between this single objective optimization and multi-objective optimization. So tasks for single objective optimization are as follows. You model the system, formulate the problem. Model the system means you must, since we are talking about mathematical optimizations, you must express the physical system we are going to optimize by mathematical equations. So these may be simple equations, these may be very complicated equations, there may be series of equations, whatever it is, we need a model for the physical system we are going to optimize. In case of in case of that simple optimization problem of designing the cylindrical vessel, that objective function was the model. So in case of more complicated problem, let us say a chemical reaction is taking place in a reactor. I need a physical model which will describe what is happening inside the reactor. And those equations will give me what is I want from this productivity. I want to maximize the purity of a product. So upon solving the equations that describe what is happening inside the reactor, I must get an answer to that question. That is, if these are the things that are changed, if certain things are changed within the reactor, this is how the purity will be affected. So basically, a mathematical model that describes the physical system. Once you are done with modeling and problem formulation, you take help of typically numerical methods for numerical optimization problems only, because for real world problems, you won't be able to solve analytically. You will be taking help of the numerical algorithms that are available for solutions of optimization problems. And typically you'll have a single solution, so you won't have any problem in implementation of that solution. But in case of multi-objective optimization problem, as one of you rightly asked, you'll have 3 tasks. Apart from this modeling, problem formulation, and optimization, you'll also have another task, which is selection of a single most preferred solution. Now, this step 2 is also different. This optimization typically leads to single solution, but here during optimization, you will get all the Pareto optimal solutions. If the optimization is successful, you will get all the Pareto optimal solutions. Now you have to select one preferred solution. So how do you select most preferred solution? See, typically there are certain methods of solving this. Okay, entropy method. Okay, the utopian point. So there are certain methods to select one of these optimal solutions from these obtained Pareto optimal solutions. But note that this always requires some other input. Let us again come back to this card purchase problem. Suppose I have been asked to help in this decision process. So a company is buying very expensive car. Okay, any car, right? So company is buying car. Okay, and I have been asked to suggest or to give this inputs for this decision making process. See, the best thing I can do is to optimal solutions as possible. Then I can choose one solutions only after receiving certain preference. That means certain additional input from the decision maker. Who is the decision maker here? The decision maker is the company who hired me to do this job. So typically, when I select the preferred solutions out of all the available non-dominated solutions, you will require higher level of information to make a suitable decision. So without consulting decision maker, without getting the preference of decision maker, I won't be able to make any comment. Let us say the decision maker tells me, so this is the maximum amount of money I have, okay, and this is the minimum level of comfort beyond which I won't go. So that will allow me now to select one of these solutions that are available. So for any problems, even say suppose we are trying to find out the optimal operating condition for a process. And if there are multiple objectives, typically there will be multiple objectives. We'll get the non-Pareto optimal solutions. We'll get the Pareto optimal solutions. And then the management must decide which operating condition to implement based on other considerations. In certain cases, it is possible to see, always such considerations cannot be put in terms of equations, but in certain cases it can be. And for that, there are some methods to find out one optimal solutions from the non-Pareto optimal form. So basically, this again describes that. So in problem formulation, then we optimize, we investigate the solutions, and then we discuss between the discussion between decision maker and the optimizer. The discussion between the decision maker and the optimizer will help to obtain a preferred solution. But yes, there are certain techniques also which can be used to obtain one of the solutions from the Pareto optimal form. But again, that will require specifying additional information after you have obtained the Pareto optimal form. So this graph shows some popularity about this multi-objective optimization problem. You can see that in last few years, the number of publications in this domain has increased like anything. So over last 10 years or so, the number of publications under this multi-objective optimization has tremendously increased. This is a recent data from this which 2022 only, and all those documents or the publications, are from all various areas like engineering, computer science, mathematics, which constitute the major part. So almost all disciplines are involved. So this shows that almost all real-life problems are practically multi-objective in nature. So let us now formally formulate the multi-objective optimization problem similar to single objective optimization problem. So what you see now is a single objective optimization problem formulation. You are minimizing the objective function subject to set of inequality and equality constants. And also these decision variables may be bounded by lower bound and upper bound, right? They are also known as box constants or bounds. Note that this is posed as a minimization problem, but any maximization problem can be converted to minimization problem by simply multiplying the objective function by -1. So minimize fx is same as maximize minus fx. So without any loss of generality, we can write this optimization problem as minimization problem, because maximization of fx is same as minimization of minus fx. So minimization problem can be converted to maximization problem, and the vice versa, simply by multiplying objective function by -1. So you already know that the solution has to satisfy these constants, and if a solution satisfies all the constants, right? This inequality constant, this equality constant, as well as these bounds, we'll call that solution as feasible solution. If not, we'll call that as infeasible solution. So how the multi-objective will be object, meaning that multi-objective optimization problems are also subject to equality constant, inequality and bounds, everything. So you will have exactly similar problem formulation with this fx, which was single function, will be now replaced by a vector of functions. So here it is assumed that I have k number of objective functions. So we are minimizing a vector for k number of objective functions simultaneously, subject to inequality constant, p number of inequality constant, m number of equality constant, as well as these many bounds on the decision variables. So in case of single objective optimization problem, whether a particular solution or proposed solution is better or not compared to another one can be easily determined by comparing the objective function value. For this, suppose I am minimizing the function. Say I have one solution here, okay, one trial solution here, another set trial solution here. You know that this is better, because you have a single objective function, so you can straight away compare. But in case of multi-objective optimization problem, first, what are those solutions? We have now understood that those are those non-dominated solutions. But how do you compare? Because the comparison has to be made with respect to all the objective functions. So here comes in this concept of dominance, from where these non-dominated solutions name has been borrowed. So in multi-objective optimization problem, the goodness or the quality of a solution is determined by the dominance. So let us see what is dominance. Yes, what is this question? How to choose one optimal solution from many optimal solution? Is there a separate mechanism from optimization? Okay, so I think we briefly discussed this. Unfortunately, we won't be able to discuss some of those methods that are used. Okay, but yes, your the primary objective of the multi-objective optimization is to obtain the Pareto optimal solutions, all the Pareto optimal solutions. Once all the Pareto optimal solutions are obtained, then you need to select one solution based on some other preference. Typically, in a say in a setup, this is known as the decision maker's preference. Okay. So in multi-objective optimization problem, the quality or goodness of a solution is determined by the dominance. Let us consider these two. We are minimizing both the objective functions. Z is objective function here. So again, we cannot say anything as to whether A is better than B or not. Because one is better with respect to one objective function, other is better in respect to other objective function. But consider these two solutions. See, always A is better. When I'm minimizing both Z1 and Z2, A is superior to B with respect to both the objective function. Here we cannot say that, but here A is always better than B. We'll call A dominates B. So the test of dominance is as follows. Pick up two solutions x1 and x2. x1 dominates x2 if the solution x1 is no worse than x2 in all objectives, and solution x1 is strictly better than x2 in at least one objective. If that is the case, we'll call x1 dominates x2. So solution x1 is no worse than solution x2 in all objectives, and solution x1 is strictly better than solution x2 in at least one objective. If both the conditions are met, we'll call x1 dominates x2. See, x1 dominates x2 is equivalent to saying x2 is dominated by x1. Now you remember we had a difficulty in combining two objective functions which are expressed in different units, different scales like that. Like say cost and comfort, how do I combine? Now here it is possible that I can compare pairs of vectors even when objectives are measured on different scales using the concept of dominance. So again, consider this example. You are maximizing F1, you are minimizing F2. Compare solution 1 with solution 2. We are maximizing F1 with respect to F1. Solution A1 is better than 2. We are minimizing F2. Solution 1 is superior. to solution 2. So solution 1 dominates solution 2. Compare 1 with 5. Both have same value for F2. So 5 is no worse than 1. But 5 has better F1 value because we are maximizing. So 5 dominates 1. What about 1 and 4? See, 1 and 4, you cannot say anything. Neither solution dominates. Because 1 has better F2, but 4 has better F1. So when you compare 1 and 4, neither solution dominates. So this dominance relation will basically give us a partial order on the set of vectors in the objective space. How? Let us say this is again those compare the same problem. This is minimization. This is okay, both minimization. Both the objective functions are minimization objective functions. So if you compare A and D, A dominates D. So this is how we can write A dominates D. D dominates E. Compare both objective functions. You see that A dominates D, D dominates E. Similarly, B dominates C. But what about A and B? Neither dominate. Because A is better in terms of Z1, whereas B is better in terms of Z2. So among all these set A, B is the non-dominated set. Other solutions or other points are dominated. So in a multi-objective optimization problem, we'll choose as many such solutions as possible. So in terms of definition, given a set of solutions, the non-dominated solution set is a set of all the solutions that are not dominated by any member of the solution set. The non-dominated set of the entire feasible decision space is called the Pareto-optimal set. And the boundary defined by the set of all points mapped from the Pareto-optimal set is called Pareto-optimal front. Okay. So all these Pareto-optimal solutions are optimal trade-offs. They're the best trade-offs. Pareto-optimal solutions are the best trade-offs. And the decision maker makes best preference and thus guide the choice of single final solution. So again, now consider this decision variable space and the objective function space. Let's consider I have this two-dimensional space and two-dimensional objective function space. There is 1:1 mapping we have discussed. So let us say these are the solutions which are Pareto-optimal solutions. So all such Pareto-optimal solutions will form this Pareto-optimal front in the objective function space. And of course, feasible objective function space. This is also feasible decision space, and this is a feasible objective function space. This is the Pareto optimal front in the feasible objective function space. Solutions which are para-optimal solutions or non-dominated solutions. So they are neither inferior nor superior when you compare all the objective functions simultaneously. So they are the trade-offs, space trade-offs for the multi-objective optimization problem. So here are some typical shape of this Pareto optimal front that you will get for, say, two objective functions problem. See, let us consider both the objective functions are minimization type. So you can consider that, you can imagine that the solutions will lie towards this, right? Origin. So perhaps this will be the Pareto optimal front. Whereas, see, if one is minimization, F1 is minimization, F2 is maximization, you may get this. And this is the nature of the region. Both the objective functions are minimization here. Here, say minimize F1, maximize F2. So minimize F1 towards this and maximize F2 towards this. So this will be the Pareto optimal front will be located here. F1 maximize, F2 minimize. You're likely to have this Pareto optimal front here. And F1 maximize, F2 maximize, you will get the Pareto optimal front here. Okay. I do not have much time left, but anyway, so we'll quickly discuss one or two important concepts. Professor Akshay, a few more minutes.
Yeah, sure. Am I audible?
Okay. Okay. So, yes. Yes. Okay. Okay. So let me just make one comment on the optimality conditions of the multi-objective optimization problem. Okay. So this itself, I think, will take maybe a couple of classes. So I'm going to do that. I'm going to show you the optimality conditions or similar conditions also is a optimization problem. So let us consider the optimization problem. And the optimality condition, that means the condition that must be satisfied for a solution to be optimal for this general optimization problem, general NLP, general nonlinear programming problem with single objective function and constants, are known as KKT conditions or Karus-Kuntaker condition. Now, I'll just tell you the key features of these KKT conditions. What you do is you first formulate something called Lagrangian function. So the Lagrangian is what? The Lagrangian is sum of this objective function and the product of multipliers of this inequality constant as well plus equality constant. How? Let me explain. So you have, I have said, you must constant. So for each p number of inequality constant, I define Lagrange multipliers. I define multipliers, p number of multipliers. For each m equality, we have m number of equality constant. So for each equality constant, I define one Lagrange multiplier. So I have p number of multiplier here. I have m number of multiplier here. These, let me call these p number of multipliers as u, and u1, u2 up to up, and these m number of multipliers for Lagrange multipliers for equality constant, let me call those, say, v1, v2, v3 up to vm. Now you have p number of inequality constants. So you take u2, g2, u3, g3 up to up-gp. Add those. Similarly, you have m number of equality constants. So v1, h1, v2, h2, v2, h3 up to vm, hm. Add those. Add it up to this objective function. This is Lagrangian. So Lagrangian now is a function of, the objective function is a function of x alone, but Lagrangian is a function of x as well as multipliers for this, multiplier for this. That means u and v. Actually, you know what? This is one way of converting, these constants into this. So I now have a Lagrangian which has actually incorporated these inequality and equality constants. So the optimality conditions now are applied on these. And you can say the conditions, the point x, which say minimizes this Lagrangian and satisfies these and some other constant, some other conditions that you will see, will also solve this problem. That means that when you find minimum for Lagrangian, there will also be minimum for this original problem. Suppose a function of single variable f of x, you said del f del x equal to 0, df dx equal to 0, right? You have multivariable functions. So del f del x1 equal to 0, del f del x2 equal to 0, so on and so forth. Instead of doing on f, you do on Lagrangian. So the gradient condition is del L del xi equal to 0. Del L del xi. So this will give you how many number of equations? You have objective function in n variables. So this derivative will be with respect to del L del x1, del L del x2 up to del L del xn. N number of equations you'll get here. So take the derivative of the Lagrangian with respect to each of these decision variables. This gives you any equations. This must be set to 0. Like del x, del x equal to 0, del x equal to 1, and so on, will also be equal to 0. Then the solution must be feasible, right? So the solution must satisfy these inequality constants. We call that feasibility check. Then there is something called switching condition. It perhaps requires some discussion, but let us assume, let us take it as it is, that the switching conditions means that the product of this multiplier of this inequality constant with this inequality constant is equal to 0 at optimality. Then there is non-negativity restrictions on the multipliers for inequality. That means this U should be greater or equal to 0. For these questions, this formulation is important. Now I have minimization problem and inequality is less or equal to type. You can always pose maximization problem or greater or equal to type into this form, and then these conditions will be applicable. Like if it is maximization problem, you just take multiply by -1 and pose it as minimization problem. If these inequality constants are greater or equal to type, multiply by -1, convert it to less or equal to type. Note that there is non-negativity restrictions on Lagrange multipliers for inequality constant, but no such restrictions for these equality constants. Lagrange multipliers for equality constants are free from sign. They can be negative. And finally, there is one important condition, which is regularity check, which says the gradients of the active constant must be linearly independent. Active constant means a constant can be satisfied as active constant or inactive constant. Consider this G less or equal to 0. So G equal to 0 is constant satisfied. G less than 0 is also constant satisfied. When G equal to 0, we call that constant being satisfied as active constant. So active constants meaning constant being satisfied like equality type. So all the gradients of such active constants must be linearly independent at optimality. So if now we consider X star is a candidate solution, that means a candidate solution for solution which will minimize this object. So that's those X star must satisfy these constant equality constants, visibility check. Those corresponding multipliers will satisfy this switching condition. UG GJ equal to 0 for all p number of equations, all p number of constants. So that means you have p equations over here. Then these multipliers associated with this are non-negative. So UJ star greater or equal to 0, and the gradients of the active constant must be linearly independent. So these are KKT conditions for any general single objective optimization problem. So the optimal solution will satisfy these constants. Okay. Now, the same conditions hold true for multi-objective optimization problem also. But now, instead of these f function over here, but these KKT conditions can also be extended to multi-objective optimization problems. You can understand that although this gives us, an analytical proof that I can show that this solution, this solution is really optimal because this satisfies KKT conditions. But it's not so easy to handle with any types of equations, because see, it is not necessary for simple functions. For any general nonlinear functions, these Lagrange will lead to set of nonlinear equations. But this theory says that these KKT conditions are optimal solutions will satisfy these KKT conditions. For simple problem, okay, that means simple problem in this sense is this, this objective function and this they may not have to be linear always, but these equations will be such that I can solve these equations. See, if these equations, these conditions, gradient conditions give me a set of equations which are solvable, I have candidate solutions on which if they check if they satisfy this visibility, if they satisfy switching condition, these conditions, and also the gradients are of the active constants are linearly independent, then I know that is a really optimal solutions because that satisfies KKT conditions. And for such general constant problems, those are known as KKT points. So an optimal solution first have to be KKT point. That means it must satisfy the KKT conditions. Again, this is only first order condition. It is like, say, you remember in your early days class, you first for a simple single variable function, you first use df dx equal to 0. Okay, then solve it, and then to say whether it is minimum or maximum or point of inflection, you take higher order, right? D square f dx square you take. Similarly, that is df dx equal to 0 first order condition. This KKT condition is also first order conditions. So higher order conditions, second order conditions needs to be applied to say whether the KKT point is really a true optimal solution or not. But we talked about convex problems, right? When the objective function is convex function and the such space defined by the inequality equality constants are convex region. For such convex problems, KKT point will always be an optimal solution. Anyway, it's not possible to go into more details of this. So I want you to know that this KKT conditions will be applicable for multi-objective optimization problems as well. Okay, we'll see that. Okay. So now we will. So let us see quickly. I think one or two methods for this multi-objective optimization. Sum convert this objective function into a single synthetic function. It may be any number of function. Here the problem is, this doesn't produce Parrot optimal solution that lie in the non-convex part of the Parrot optimal form. It works best only for convex regions. Also, a set of distributed weights, lambda 1 is our weight here, corresponding to W. A set of evenly distributed weights doesn't guarantee that you get an evenly distributed Parrot optimal form. So works best for the convex region. See? Evenly distributed weights doesn't guarantee form. You get solutions here, you get solutions, then you don't get solution here. The convex region, it cannot find solution. This problem cannot be solved for this convex region because the paratophone are not minimum of any weighted sum. Another method is known as epsilon constant method. Here, as we discussed, that you select one objective, all objective functions into constants, and you specify bounds on them. So choose one objective function to minimize, and then you put bounds on all other constants. Now you solve it as a single objective optimization problem, each time with various values of these bounds. And then it is possible to obtain the Parrot optimal form even for non-convex problems. So the weighted sum actually does not work. Non-convex region works. But here, see, each time you have to consider one value of the epsilon and you will get 1 point. Now, what can be a better way of solving multi-objective optimization problem? obviously those optimization techniques which will give me all the Pareto optimal solutions in one go, in one run of the algorithm. And you already know that there is something called genetic algorithm which does this job. I think you already had a class on this genetic algorithm. So variant of genetic algorithm only, which has been adapted for this solutions of multi-objective optimization problem. One very popular such genetic algorithm is known as non-dominated sorting genetic algorithm, or NSGA. NSGA 2. NSGA first NSGA was proposed by, again, Professor Kullan Day, and then a much more improved version was proposed, which we call NSGA 2, which is very popular. In fact, currently another version of NSGA is also available. So we want to
Hello. Hello. Am I audible to the participants?
Yes, sir. You are audible, but the
But
voice is
Professor
not
Sarkar
coming
is
with
not,
this.
right?
Yes, sir. Exactly.
Let me call him. Acha, I think he vanished. So he had some internet connectivity issues.
Yes, sir.
Let me call him.
again, is it? Is it visible?
Yes, sir. It's visible.
Yes, sir. Yes, sir.
Okay. So I think I got disconnected. I didn't know, in fact. I think I was discussing here.
Yes, sir.
Yes, sir. Yes.
Okay, fine. Okay.
I'll disconnect the phone now.
Yes. Okay. Okay. So I have taken a lot of time.
No, it's okay. It's okay. It's fine.
Anyway.
Completely fine.
Okay, fine. Okay, so what I was saying that you are already familiar with genetic algorithm, and you have seen that it always poses a population of solution, and that feature is very attractive for solving multi-objective optimization because you are going to get you're looking for a set of Pareto optimal solutions, non-dominated solutions. So, so this NSGA2, again proposed by Professor Kallanmoy Dev, is one of the most, is a powerful multi-objective optimization algorithm, and has been widely used. Okay, the source codes are also available, so you can work with this. And this MATLAB implementation, this GA multi OBG also uses this NSGA2. They write a variant of NSGA2, maybe slight changes from the small changes from the original formulation or algorithm. So, see, in case in NSGA2, if you just remember that genetic algorithm starts with a collection of trial solutions, we call those as initial population, and then with every iteration, it uses certain genetic operators known as crossover mutation. It is like getting a improved solution from a trial solution using those operators. And with every iteration, you go from better to better solutions. I mean, NSGA2 will also do the same thing, but additionally, it has this implementation of this non-dominated sorting. That means a very efficient search technique to sort out, to get those non-dominated solutions at every iteration. And then finally, we get these Pareto optimal solutions. So we won't discuss NSGA2 in more detail, but let me now show you its MATLAB implementation, which is called GA multi OBG. So this GA multi OBG, if you have access to MATLAB, please type help GA multi OBG. You will get all these informations. So this I have taken from the MATLAB help only. So let us first quickly go through the syntax, okay, so that you can start using it. So GA multi OBG is the function name which implements, let us say, NSGA2 algorithm or a variant of NSGA2 algorithm. It is in fact an NSGA2 algorithm, maybe with some modifications, for solutions of multi-objective optimization problem. So this is the minimum syntax that is required. Okay, so this is the minimum syntax that is required. X is what X will contain the solutions of this multi-objective optimization problem. So let us consider you have a multi-objective optimization problem. Consider the simplest case. You simply have two functions. F1 equal to something, F2 equal to something. F1 is a function of x1 and x2. F2 is also a function of x1 and x2. That's all. You do not have any constant, nothing. So this statement, this syntax is enough to solve that problem. So this function which solves the multi-object optimization problem, will take on various number of inputs depending on the kind of problem you have in hand. So if you write this, it will solve the non-nominated solutions X or the Pareto-optimal solution X for the problem written in this function called FUN. So FUN is the name or handle of a function where you have written those two functions which you are simultaneously maximizing or minimizing, or one minimizing, one maximizing. Inverse is the number of variables. So you have two variables, inverse equal to 2. Now, this next one, you see there are two additional arguments, capital A, small b. Capital A and small b you will require when you have linear inequalities in your problem. Linear inequalities will be expressed in terms of Ax less or equal to b. So A will be a matrix, X will be a vector, B will be a vector. Similarly, if you have linear equality constants, you will have another two argument, and the constant will be written like this, right? A equality into X equal to B equality. Ax equal to B, Ax equal to B, that the matrix equation you imagine. So this is inequality constants, but all linear. Ax less or equal to B, Ax equal to B. So A and B, so A is the coefficient of that matrix. B is that right hand side vector. Similarly, this is the coefficient of that matrix of all these linear equality constants, and B equality is the right hand side vector. Remember, these are linear, and that's why you're able to write like this. Now, if you have lower bounds and upper bounds on these decision variables, then you use lower bound and upper bound. So lower bound will be a vector. If you have two variables, x1 and x2, lower bound will be a vector where each element will be the lower bound for each decision variable. The same thing is for upper bound UB. Now, next one is see another argument known as NONL con. It is basically non-linear constant. So we have now, as of now, we have seen no constant, then linear inequality constant, linear equality constant, lower bound, upper bound. That means those bounds are decision variable. Now, non-linear constants. So non-linear constants are of this type: C less or equal to 0 or C equality equal to 0. Non-linear constants can be both equality type and inequality type, but they will be handled in the same function. So non-L con is basically another function like fun where you have to write the nonlinear constants, and this function will return this C and C equality. C for nonlinear inequality constant, C EQ is for nonlinear equality constant, and both the nonlinear inequality and equality constant will be strictly written as C less or equal to 0 or C equality equal to 0. Here you won't have problem between sign, I mean equality inequality sign, but here you see less or equal to type. So if you have a constant of greater or equal to type, you multiply that by -1 to convert it to less or equal to 0 type. Imagine in a problem you have nonlinear constants, but say you do not have these linear inequality constant or linear equality constant. So these must be replaced by empty matrix. Because it is very important to put the arguments in this sequence only. Here you have little bit, difference, these options. If you do not have non-LL con, you can put options here. But if you have nonlinear constants, you have to give nonlinear constant first, then put options. Options is basically a structure with which you can give additional instruction to the optimizer, like it is a genetic algorithm code. So suppose you have to change the default value of the number of iterations. You can set that. You can ask the algorithm to print the solutions at every iteration. So this is a structure which is used to give more instructions or instruction when you want to change some of these default settings. The current implementation of this GA multi-OBG also allow you to use constants which are of integer type. So if some constants are integer type, this intcon, in this intcon, you will list those variables which will take integer values. Like these arguments here, these are the inputs to the function, right? And similarly, it doesn't return only the Pareto optimal solutions, but it also returns the function values. Okay, it also returns the function values. It can also return an exit flag, which will basically it returns an integer, which will tell you, whether the algorithm converged. Okay, whether the reason for the algorithm stop, basically whether the algorithm converged or not converged, or what is the reason for stopping, so on and so forth. And output is a structure which contains information about the optimization process. Population, it is a matrix whose rows are the final population, and scores contains scores of the final population. Scores means the fitness function values, right? So this is how you can make use of this multi-objective GA function that is available with MATLAB. Depending on whether you have equality constant, inequality constant, equality constant, linear inequality constant, linear equality constant, or nonlinear constants, you have to select one of these syntax, because it is, and if suppose it is, this is present, but this is, these two not present, it cannot be like this is present and this is not, right? I mean, either A, if A is present, A and B will be present, right? So if this is present but this is not, this must be replaced by empty matrix. Okay, so similarly, output also, it will be, obviously it will return you the Pareto optimal solutions. It will also return you the objective function values of those Pareto optimal solution. So now let me take a simple example and see how it works. So let us consider the problem that I started with, but instead of cylinder, let us take a cone. So this this slanting this side can be written as this, right? If this is r and this is h, L equal to square root of r square plus h square. The volume of this cone is 1/3 pi r square h. This base area is pi r square. This lateral surface area is pi r l. So total area is this, pi r square plus pi r l. Now the multi-objective optimization problem we are proposing is minimize S, that means the base area, sorry, this lateral surface area, and minimize the total area. Okay, so we have, let us have this, both the objective function, minimize lateral surface area and minimize the total area, subject to the constant that the volume of this cone must be greater or equal to 200 centimeter cube. Sorry, this will be centimeter cube. So the radius, let us say, will lie between 0 to 10 and height will lie between 0 to 20. So these are like bounds. So now you see, you can have various cones, right? With some cone, large base, okay? Some cone, small base, more height, corresponding to these two objectives. So how will you solve this problem using MATLAB function GA multi OBJ? I have number of variables 2, R and H. I do not have linear inequality constants, so represent them by empty matrix. Similarly, I do not have equality constants. See, volume is greater or equal to 200 centimeter cube is basically a nonlinear constant, because volume is that, you know, that is a nonlinear relation between R and H. Lower bounds, both the lower bounds are 0, R and H, R upper bound, H upper bound. So this is a options, you know, structure, which basically says that this algorithm, okay, you have to plot function. That means you will plot this Pareto optimal front at each iterations, population size 100. You may not even use this, so then you will simply drop this. Now you use these. I have nonlinear constants, and I'm also using options, so I'll use this. But here I will also use this, or maybe even these. So first argument is the name of the function, where we'll write those two objective functions: minimize S, minimize T, minimize the lateral area, minimize the total area. So expression for the lateral area, expression for the total area. Those are two different objective functions. Inverse equal to 2. A, B, null, null, empty. A equality, B equal to empty. Lower bound, upper bound specified. This is the function where I have to write nonlinear constant. And this is the options. If you do not have this, you can just simply drop it. So it tells you that 100 population size. That means the GA and SGA will start with 100 trial solutions, and it will plot the results at every iteration. Okay, this I have written just to, you know, show the results. So this will show you R and H, their function values for R, function value for AH, and this, you know, this that pi r square H by 3, right? So also give the volume. So volume we are trying to get V greater or equal to 200. So my solutions to show the volumes are about greater or equal to 200. This itself will plot the Pareto optimal front, but you can also ask MATLAB to plot. So plot f val, right? F value, function value. So this will have two rows, two columns, right? One is for each one for two objective functions, right? So F1 versus F2. So now see how you write these two functions, this function and this function. So this function will return y, which is nothing but this, a vector whose components are the values of the objective functions. X will be finally the Pareto optimal solutions, right? So it will contain values for R, values for H. So the way I have defined, the first one is the R, second one is the H. Pi r square, the base area, lateral area. Okay. and then pi L. Okay, L is that slanting height, and S is the lateral area, pi L, total area. So I want to minimize. I am minimizing. Okay, here I am minimizing base area. It's okay. So if you are using base area, and if you are using this lateral area, you put S here. If you are using only the base area, you put B here. Okay, fine. And then the total area, the second objective. So note, whatever complicated the function, your function is, that means you may be solving a very complex physical system. So these function will contain the equations or the model for that system. Format syntax is same. So this is a problem which is very simple, but shows you exactly the same syntax that needs to be followed even for a complex optimization problem, because it has it doesn't have equality inequality constants, linear inequality, linear equality constant, but it has nonlinear constants also. So this is the nonlinear constants, which says the volume should be greater or equal to 200. So C less or equal to 0. This should be the format, right? So see, this has to be then expressed C equal to 200 minus V. So first C and CQ. CQ I do not have any equality nonlinear constant. So this should be empty. I have C. C is what? C less or C of X less or equal to 0. It says that the volume should be greater or equal to 200. So V should be greater or equal to 200. So C should be C less or equal to 0. I have to write. So C will be 200 minus V. So V is greater or equal to 200. So 200 minus V is greater or equal to 0. So V minus 200 is less or equal to 0. So C equal to 200 minus V. So you calculate V in this function. That's all. So now we have already called this function. So if you now run it, you'll get this solution. So this is the Pareto optimal front. Okay. So each point on these front is a Pareto optimal solution. So these solutions will vary from cones with large base, small height, to cone with small base, large height. Again comes to the same question. So which cone should I choose? Note that I need another preference from you to answer that question. So that is decision maker's choice. Which again, there are certain techniques which can be done using automatically using programs. Okay. But unfortunately, we are not going to discuss those short of time. So this is basically this syntax, this format can be used for solving almost any multi-objective optimization problem that can be solved using GA multi-OBJ with appropriate values of those arguments. So this is all from my side. But before I leave, I'll also show you. Let me run that. Okay, so is my MATLAB screen visible?
Yes, it is.
Okay. So basically, see, I've actually copied and pasted from this my MATLAB code onto this PPT. So all these things, right? So I'm writing, I'm defining number of variables, A, B, A equality, B equality, lower bound, upper bound, options, then calling the function. Okay, just writing to show you the values, right? And then this function, see, okay, this function, which basically describes those two objective function, and this is a nonlinear constant. Functions for the nonlinear constant, C less or equal to 0. Functions we have is C V greater or equal to 200. So you can imagine the solution that volume will actually be very close to 200, right? Because you are minimizing both the areas, base area or the lateral area and the total area. I'm solving here for base area and the total area. So obviously the volume, if I pose a restriction like V should be greater or equal to 200, B should be around 200 only. Because if it goes higher, then that will maximize, that will increase the area. Okay, so now let us run this program. Is it visible? Is it now? Is it visible? The Pareto front is visible.
Yes. Yes.
Yeah. So yes. So this is because that another set of comments I gave to write this. So you have obtained this Pareto optimal front. Actually, this is same as this. Okay. So I can actually. So this is the Pareto optimal front is obtained. So each point on this solution basically corresponds to one R and one H for a cone. So each point corresponds to a new design. Each point corresponds to a different design. And just to get those values, you see, these are the values. So this is R, this is H. So this is the, that one objective function. This is the another objective function. So this is the base area, this is the total area, and this is the volume. See, the volumes are all close to 200 because of the, it was given V greater or equal to 200, but it cannot be very high. It cannot be higher than much higher than 200 because then it will maximize the lateral area. So ideally it will be very close to 200 or even 200. Okay, so this is how you can solve a multi-objective optimization problem. If you're interested, I suggest you please explore the MATLAB GA multi-OBG and the code that I used. This can be used for solutions of any such problem. Note that A and B, if you have A and B, so this is the maximum functions that you need to have to written. If you have the equality constant, linear inequality constant, linear equality constant, those things needs to be defined here only as matrix form, right? AX less or equal to B, or A equality X equal to B equality. So that's all from my side. So sorry for taking almost 1 hour extra. If you have any question, maybe I'll be trying to answer that question. Thank you very much for giving so much time to me.
Thank you, Professor Sarkar, for going into so much detail. It is actually, we should have given you 2 slots. Had I known, I would have fixed 2 slots for you. You actually, I mean, would have been better that way. Thanks for going into all these details. Now, participants, if you have any questions, please let us know at this stage. No questions? Okay, if participants don't have the question, then I guess we should close the session today. Yes?
Okay.
Okay. Thank you, Professor Sarkar. Tomorrow again you have a session.
Tomorrow, I think tomorrow I'll keep myself to 1.5 hours or maximum 2 hours. Well, there is some comment. Somebody wanted to get some code. Is it okay? I'll give that. No problem. I'll do that. He wants this code to be uploaded somewhere, or
you can just paste it in the chat box if you don't have any problem. He can. Is it fine, Ashish? Is it fine if we can paste the code in the chat box?
Or I can send?
Sure. So whatever is comfortable to you, Professor. You can paste it here, or you can send it to me and I'll email them.
Okay. I think that will be better.
Okay, sure. I'll email them.
There are 2 files. I don't know whether that will be.
Sure. So I'll
email it to you.
Okay.
I'll email it to you. You please email to the participant.
Sure.
Okay. Okay, then thank you very much.
Thank you, Professor Sarkar.
Thank you very much. Okay. I'll tomorrow, I think, yeah, we have to keep time. Okay.
So we'll again see Professor Sarkar tomorrow at 5 p.m. Please don't miss it.
5 p.m. No, we have tomorrow 5 p.m.
I think you have.
Yeah. Tomorrow 5. No, tomorrow 5 p.m. Yes, 5 p.m.
Yeah.
Tomorrow 5 to 6:30 slot I have. Okay.
Yes.
Yeah, because there is another talk. After that, I do not have this liberty of taking extra tomorrow. I'll keep that in mind. Thank you very much.
Thank you, sir. Thank you.
Okay.
Okay. Thanks, participants. See you tomorrow. So I'll close the session now.